Yes, it is possible to have both emergency power and commercial power in the same electrical box in a hospital setting. This is commonly achieved using a transfer switch. A transfer switch is an electrical device that automatically switches between two power sources. In this case, the transfer switch would be used to switch between the commercial power grid and the emergency generator. When the commercial power grid is available, the transfer switch connects the electrical system to the grid. If the commercial power fails, the transfer switch automatically detects the outage and switches the system over to the emergency generator. When the commercial power is restored, the transfer switch switches back to the grid, providing seamless power. Having both emergency and commercial power provides redundancy in the event of a power outage. The transfer switch ensures uninterrupted power supply to critical areas of the hospital, such as the operating rooms, intensive care unit, and emergency department. The transfer switch isolates the emergency power system from the commercial grid, preventing potential electrical hazards. Proper installation and maintenance of the transfer switch and electrical system are crucial for safety. Clear labeling and signage should be used to indicate the sources of power and the operation of the transfer switch. Regular testing and inspection of the system is essential to ensure its functionality in an emergency. In a hospital environment, the electrical system is critically important, and the integration of both normal and emergency power sources requires careful planning and adherence to safety standards. Let's explore the key aspects of this integration, focusing on transfer switches and their role in ensuring a reliable power supply. Firstly, the National Electrical Code, or NEC, provides guidelines for the installation and operation of emergency power systems. These guidelines are designed to ensure the safety of patients, staff, and visitors in the event of a power outage. Secondly, transfer switches are essential components in systems with both normal and emergency power. These devices automatically switch between the normal power source and the emergency generator, ensuring that critical loads remain powered during an outage. There are two main types of transfer switches: automatic transfer switches, or ATSs, and manual transfer switches. ATS automatically detect a power outage and switch to the emergency generator, while manual transfer switches require human intervention. Thirdly, hospitals typically use ATS because they provide a seamless transition to emergency power. This is particularly important in areas such as operating rooms and intensive care units, where even a brief interruption of power can have serious consequences. When selecting a transfer switch, it is important to consider the load requirements of the critical equipment that will be powered by the emergency generator. The transfer switch must be sized appropriately to handle the maximum current and voltage of these loads. Additionally, the transfer switch must be listed and labeled by a recognized testing laboratory, such as Underwriters Laboratories, or all, to ensure that it meets safety standards. The installation of a transfer switch must be performed by a qualified electrician in accordance with the NEC and local codes. The electrician must ensure that the transfer switch is properly grounded and that all connections are tight and secure. Additionally, the electrician must verify that the transfer switch is functioning correctly and that it switches to the emergency generator when normal power is lost. Regular maintenance is essential to ensure the reliable operation of a transfer switch. This includes inspecting the switch for signs of wear and tear, cleaning the contacts, and testing the switch to verify that it switches to the emergency generator when normal power is lost. Hospitals should also have a written emergency power plan that outlines the procedures to be followed in the event of a power outage. This plan should include instructions for operating the transfer switch, starting the emergency generator, and notifying key personnel. The plan should be reviewed and updated regularly to ensure that it remains current and effective. In addition to transfer switches, other important components of a hospital's electrical system include emergency generators, uninterruptible power supplies, or UPSs, and surge protective devices, or SPDs. Emergency generators provide a backup source of power in the event of a prolonged power outage. UPS provides short-term power to critical equipment such as computers and medical devices, allowing them to continue operating during a brief power interruption. SPD protect electrical equipment from damage caused by voltage surges. The design and installation of a hospital's electrical system must take into account the specific needs of the facility. This includes the number of patients, the types of medical services provided, and the local climate. The electrical system must also be designed to meet the requirements of the NEC and other applicable codes. Hospitals are required to perform regular testing of their emergency power systems to ensure that they are functioning properly. This testing includes load bank testing, which simulates a power outage and verifies that the emergency generator can supply power to the critical loads. Hospitals must also keep detailed records of all testing and maintenance activities. These records must be available for inspection by regulatory agencies. In summary, the integration of normal and emergency power sources in a hospital requires careful planning, proper installation, and regular maintenance. Transfer switches are essential components of this integration, ensuring that critical loads remain powered during an outage. By following the guidelines of the NEC and other applicable codes, hospitals can ensure the safety and reliability of their electrical systems. Now, let's dive deeper into the technical aspects of integrating emergency and commercial power in a hospital setting. We'll examine the different types of transfer switches, wiring configurations, and safety considerations that are essential for a reliable and safe power system. Firstly, let's discuss the types of transfer switches. As mentioned earlier, there are automatic and manual transfer switches. However, within these categories there are further distinctions. Automatic transfer switches can be further classified as open transition, closed transition, and soft loading transfer switches. Open transition transfer switches, also known as break before make transfer switches, briefly interrupt power to the load during the transfer process. This type of switch is suitable for most applications where a short power interruption is acceptable. Closed transition transfer switches, also known as make before break transfer switches, momentarily connect both the normal and emergency power sources to the load during the transfer process. This type of switch is used in applications where even a brief power interruption cannot be tolerated. Soft loading transfer switches gradually transfer the load between the normal and emergency power sources. This type of switch is used to minimize stress on the generator and connected equipment. Secondly, wiring configurations play a crucial role in the integration of emergency and commercial power. The wiring configuration must be designed to ensure that the emergency power system can supply power to the critical loads in a safe and reliable manner. One common wiring configuration is the separately derived system. In this configuration, the emergency generator is connected to a separate transfer switch that is isolated from the normal power system. This configuration provides a high level of isolation between the two power sources, which is important for safety. Another common wiring configuration is the non-separately derived system. In this configuration, the emergency generator is connected to the same transfer switch as the normal power system. This configuration is less expensive than the separately derived system, but it does not provide the same level of isolation between the two power sources. Thirdly, safety considerations are paramount when integrating emergency and commercial power. The electrical system must be designed and installed to minimize the risk of electrical shock, fire, and other hazards. One important safety consideration is grounding. The grounding system must be designed to ensure that all metal parts of the electrical system are properly grounded. This helps to prevent electrical shock in the event of a fault. Another important safety consideration is overcurrent protection. Overcurrent protective devices, such as circuit breakers and fuses, must be installed to protect the electrical system from damage caused by overloads and short circuits. The NEC provides detailed requirements for grounding and overcurrent protection. In addition to these basic safety considerations, there are other factors that must be taken into account when designing and installing a hospital's electrical system. These factors include the type of equipment that will be powered by the emergency generator, the size of the emergency generator, and the location of the emergency generator. Hospitals typically have a variety of critical loads that must be powered by the emergency generator. These loads include operating rooms, intensive care units, emergency departments, and life support systems. The emergency generator must be sized appropriately to handle the maximum demand of these loads. The location of the emergency generator is also an important consideration. The generator must be located in a well-ventilated area and protected from the elements. It must also be located away from areas where it could pose a hazard to patients or staff. Regular testing and maintenance are essential to ensure the reliable operation of a hospital's emergency power system. The emergency generator should be tested regularly under a load to verify that it can supply power to the critical loads. The transfer switch should also be tested regularly to verify that it switches to the emergency generator where normal power is lost. Hospitals should also have a written emergency power plan that outlines the procedures to be followed in the event of a power outage. This plan should include instructions for operating the transfer switch, starting the emergency generator, and notifying key personnel. The plan should be reviewed and updated regularly to ensure that it remains current and effective. Furthermore, consider the specific requirements outlined in NFPA 99, which covers healthcare facilities. This standard addresses essential electrical systems and provides guidance on the performance, maintenance, and testing of emergency power systems. The standard specifies different types of essential electrical systems based on the criticality of the loads they serve. These systems include the emergency system, the equipment system, and the critical branch. The emergency system provides power to loads that are essential for the safety of patients and staff, such as lighting, fire alarms, and communication systems. The equipment system provides power to equipment that is necessary for patient care, such as medical imaging equipment and laboratory equipment. The critical branch provides power to loads that are essential for the operation of the facility, such as HVAC systems and data processing equipment. NFPA 99 also specifies the types of transfer switches that are permitted for use in healthcare facilities. Automatic transfer switches are required for most essential electrical systems, while manual transfer switches are permitted only for certain non-critical loads. The standard also includes requirements for the testing and maintenance of emergency power systems. Emergency generators must be tested monthly under load, and transfer switches must be tested annually. In addition to NFPA 99, other relevant standards and codes include the International Building Code, or IC, and the International Fire Code, or IFC. The IBC includes requirements for the design and construction of healthcare facilities, while the IFC includes requirements for fire safety. These codes and standards work together to ensure the safety and reliability of healthcare facilities. When designing and installing an emergency power system in a hospital, it is important to consult with qualified engineers and contractors who have experience in healthcare facilities. These professionals can help to ensure that the system meets all applicable codes and standards and that it is properly designed and installed to meet the specific needs of the facility. They can also provide guidance on the selection of equipment and the development of an emergency power plan. In conclusion, the integration of emergency and commercial power in a hospital setting is a complex process that requires careful planning, proper installation, and regular maintenance. By following the guidelines of the NEC, NFPA 99, and other applicable codes and standards, hospitals can ensure the safety and reliability of their electrical systems. This will help to protect patients, staff, and visitors in the event of a power outage. The choice of transfer switch depends heavily on the hospital's specific needs and risk tolerance. Open transition switches are generally more cost-effective and suitable for applications where a brief power interruption is acceptable. Closed transition switches, while more expensive, are necessary for critical applications where even a momentary loss of power can have serious consequences. Soft-loading transfer switches are a good option for facilities that want to minimize stress on their generators and connected equipment. The wiring configuration should be selected based on the level of isolation required between the normal and emergency power systems. Separately derived systems provide a higher level of isolation, while non-separately derived systems are less expensive. The grounding system must be designed to ensure that all metal parts of the electrical system are properly grounded. This helps to prevent electrical shock in the event of a fault. Overcurrent protective devices must be installed to protect the electrical system from damage caused by overloads and short circuits. The NEC provides detailed requirements for grounding and overcurrent protection. In addition to these basic safety considerations, there are other factors that must be taken into account when designing and installing a hospital's electrical system. These factors include the type of equipment that will be powered by the emergency generator, the size of the emergency generator, and the location of the emergency generator. Hospitals typically have a variety of critical loads that must be powered by the emergency generator. These loads include operating rooms, intensive care units, emergency departments, and life support systems. The emergency generator must be sized appropriately to handle the maximum demand of these loads. The location of the emergency generator is also an important consideration. The generator must be located in a well-ventilated area and protected from the elements. It must also be located away from areas where it could pose a hazard to patients or staff. Furthermore, routine inspection should include checking for any signs of damage or wear on the transfer switch, the generator, and other components of the emergency power system. It is also important to verify that the batteries for the generator's starting system are in good condition and fully charged. In addition to monthly load bank testing and annual transfer switch testing, hospitals should also perform regular visual inspections of their emergency power systems. These inspections should include checking for any signs of damage or wear on the transfer switch, the generator, and other components of the emergency power system. It is also important to verify that the batteries for the generator's starting system are in good condition and fully charged. The emergency power plan should be reviewed and updated regularly to ensure that it remains current and effective. The plan should include instructions for operating the transfer switch, starting the emergency generator, and notifying key personnel. It should also include procedures for dealing with different types of power outages, such as those caused by natural disasters or equipment failures. In addition to the technical aspects of integrating emergency and commercial power, it is also important to consider the human factors. Hospital staff must be properly trained on the operation of the emergency power system and the procedures to be followed in the event of a power outage. This training should include hands-on experience with the transfer switch and the emergency generator. Staff should also be familiar with the emergency power plan and their roles in the event of a power outage. Effective communication is also essential during a power outage. Hospital staff must be able to communicate with each other and with outside agencies, such as the utility company and emergency responders. The hospital should have a backup communication system in place in case the normal communication system fails. It's also worth noting that modern hospitals are increasingly incorporating smart grid technologies into their electrical systems. These technologies can help to improve the reliability and efficiency of the emergency power system. For example, smart grid technologies can be used to automatically shed non-critical loads during a power outage, which can help to extend the runtime of the emergency generator. They can also be used to monitor the performance of the emergency power system and to identify potential problems before they lead to a power outage. Additionally, the use of renewable energy sources, such as solar panels and wind turbines, is becoming more common in hospitals. These sources can help to reduce the hospital's reliance on the commercial power grid and to improve the resilience of the emergency power system. However, the integration of renewable energy sources into a hospital's electrical system requires careful planning and coordination with the utility company. This is to ensure that the renewable energy sources do not interfere with the operation of the commercial power grid. Furthermore, the emergency power system must be designed to be compatible with the renewable energy sources. Finally, keep in mind that the specific requirements for emergency power systems in hospitals can vary depending on the location of the facility. Local codes and regulations may impose additional requirements beyond those specified in the NEC and NFPA 99. It is important to consult with local authorities to determine the specific requirements that apply to a particular facility. By carefully considering all of these factors, hospitals can ensure that their emergency power systems are designed, installed, and maintained to provide a safe and reliable source of power in the event of a power outage. This will help to protect patients, staff, and visitors, and to ensure that the hospital can continue to provide critical care services during an emergency.